Ladies and gentlemen, welcome to our first exercise on multi-objective optimization methods in Grasshopper. We start with an example for non-conflicting multi-objectives, respectively for considering more than one fitness function, fitness landscape for our problem. Therefore, please open the file 190424 enclosing circle underline multi-objective. If you open it, you see two parts, the blue boxed part of the definition and at the bottom below the pink one. We need the blue one for our first example, considering the non-conflicting multi-objective landscapes. So the example is again that we start with a set of randomly generated points. Here we use 20. You can change this value, doesn't matter. You can also change the seed, then you create a different set of the 20 points, or 20 different random points. And the rest is already known by our example for introducing the optimization methods in general. Here in the following I just separated different objectives. So objective 1 is the one that you already know. We compute the area of our minimal enclosing circle, and as you remember, we do this here in a kind of brute force method where we compute how many 10,000 values, so 10,000 circles in a grid above this random point cloud, and we select here the minimal circle. We do this to compute the fitness landscape, which is shown here. So here we can see that the most optimal solutions are in the center, or relatively in the center of our area that corresponds to the rectangle that we use to generate our points. So you will see if we change the random seed, so if we compute a different set of random distributed points, the fitness landscape will look a little bit different. So we have to wait until it computes the 10,000 circles. And now you see it changed a little bit, but in principle it's very similar. We have an area in the middle where we find the optimal center points for our minimal enclosing circle. Now I added a second objective. This is relatively trivial. We compute the middle point of our point cloud, so we just take all x coordinates and compute the average, and all y coordinates and compute the average. And then we compute the distance from this average to our center point of our minimal enclosing circle. And we define here that this circle point shall be in, or as close as possible to, the center of the point cloud. If we do this, we can compute a separate fitness landscape where we have the optimal solution for the center point of our minimal enclosing circle in the center of the point cloud, which is more or less in the center of this rectangle. And if we compare both, they don't seem to contradict with each other. We can also look into the 3D representation of these 3D spheres, and what we can do as well is that we let them overlap. So here you see the peak of these two fitness landscape, respectively the lowest point of the valley, is at more or less at the same area. Okay, just for visualization, I put them beside each other, and we look at them in 2D, which is somehow better to understand. And finally, we have a third objective where we compute the average distance of all points to the edge of our minimal bounding circle, which is, if you just look at the third objective value and its fitness function, again very close. So the optimal solution for the center point here is very close to the others. So I just added this as an example that you can in principle add many objectives. Doesn't matter. So here we consider on 2 because this is sufficient for looking into the example how to solve this problem. Just before we continue, I wanted to show you here that later we need a script for normalizing a set of values. Means we define that the maximum value is 1 and the minimum value is 0 of a range of values. Here we do this with a list and a simple C# script. When I open the C# script, here you see the short code for normalizing a list of double values that I read into my component, and I return a normalized list, normalized in array A and normalized in array B. So it differs that in the norm list A returns a series of values between 0 for the minimum value and 1 for the maximum value, and all the other values are scaled to fit in between 0 and 1. In the second normalization variant, we normalize the values in a way that the sum of all values equals to 1. So these are just two different ways of normalizing it. Here you see the formulas for this normalization. It's very simple and defined in the comments. So you should have no problem understanding this based on your C# knowledge from the other courses. Just here to prove that this is true what I told you, we sort the list of our fitness values, and here you see the smallest one is 0, and then all the other values are scaled in the range between 0 and 1 for the 10,000th value. With this, we have looked into everything that's needed to get an idea of non-conflicting objective values. Here we don't need to run the optimization. We can do this later when we look into the Galapagos optimization. But here it's clear we can easily find one optimal solution because it is more or less the same solution for both objectives in terms of the design or search space. We continue in the next example with looking into the preference-based optimization for our multi-objective problem.